Hello friends, so today we are going to discuss 2023 questions. So there are total number of 16 questions and all these questions are from mains, and this is part 2 of this 2023 questions. Okay, we have already discussed the part 1, which consists of mains as well as the advanced questions from the year 2023. So in the first question, a beam of light consisting of two wavelengths 7000 angstrom and 5500 angstrom is used to obtain interference pattern in Young's double slit experiment. The distance between the slits is 2.5 millimeter and the distance between the plane of slit and the screen is 150 centimeter. The least distance from the central fringe, where the bright fringe is due to both wavelengths coincide, is n into 10 to the power minus 5 meters. The value of n is. So we have to find out the distance, or rather least distance, that will be from central bright fringe where both wavelengths are going to coincide. Okay. So it means there will be maximum for first wavelength as well as maximum for the second wavelength. So we start from there only and we say let n1 be the maxima for 7000 angstrom and n2 be the maximum for 5500 angstroms, and for these two values they coincide. Therefore we can write the equation that n1 beta 1 will be equal to n2 times beta 2, and beta, we already know the formula, is given as capital D multiplied by lambda and multiplied by small d. So from here it is clear that beta is directly proportional to lambda, because these two values capital D and small d is fixed for both the wavelengths. So beta is directly proportional to our lambda. So therefore we can write that beta 1 is directly proportional to lambda 1 and beta 2 is directly proportional to lambda 2. So we can find out the ratio. We can write our beta 1 divided by beta 2 will be equal to lambda 1 divided by lambda 2, and lambda 1 is our 7000 and lambda 2 is our 5500. Okay. So from here this 20 goes away and we can write this as, this will be coming as 11 and this will be coming as 1 and it will be 14. So this will be 14 by 11. So we found out the ratio of our 14 by 11 beta 1 and beta 2. This is beta 1 divided by beta 2, and also we know that our y is equal to our n1 beta 1, and this can be written as n1 lambda 1 capital D divided by small d. And for the other wavelength, let us call this as y1. Similarly, we can write it y2 will be n2 beta 2, and this comes n2 lambda 2 capital D divided by small d. Okay. So now we have to find out what will be the ratio. So we can say our n1 upon n2 will be equal to beta 2 upon beta 1, and this will be giving us lambda 2 upon lambda 1, and we just found out this is equal to 11 by 14. So we get n1 upon n2 is equal to 11 upon 14. So from here we can say that the 11th maxima of 7000 angstrom coincide with the 14th maxima of 5500. So from here we can say that 11th maxima of 7000 coincides with 14th maxima for 5500 angstrom. Okay. And we need to find out the least distance. Okay. So the least distance will be given as y1, and which we wrote it as n1 lambda 1 capital D upon small d. Okay. We know all these values and we substitute it. We get this as n1 is our 11 multiplied by lambda 1 is our 7000 angstrom minus 10, this comes as 150 into 10 to the power minus 2, and small d is our 2.5 into 10 to the power minus 3. So this gives us that y1 is equal to 462 into 10 to the power minus 5 meters. And we are also given that this distance is equivalent to n times 10 to the power minus 5. So this gives us that the value of n will be equal to 462. So value of n is 462. Next question. We are given the width of fringe is 2 mm on the screen in a double slit experiment for the light of wavelength 400 nanometer. The width of fringe for the light of wavelength 600 nanometer will be. So this question is directly based on the formula that our fringe width, which is our beta, is equal to d lambda upon small d. So for two wavelengths we can write this as, or from here we can write that beta is directly proportional to our lambda. Therefore we can say our beta 1 upon beta 2 is equal to lambda 1 upon lambda 2, and fringe width of 2 mm is given to us for the wavelength of 400. So we can say this divided by our beta 2, wavelength is 400 nanometer, and other one lambda 2 is about 600 nanometer, and the 0 goes with zeros, and 2 goes with this 2, and this goes by 3. So from here we can say that our beta 2 is equal to 3 millimeters. So option number 3 is the correct one. Option 3 is correct. Next question, and it states that unpolarized light of intensity 32 watt per meter square passes through a combination of 3 polarides such that the pass axis of last polaroid is perpendicular to that of the pass axis of the first polaroid. If the intensity of emerging light is 3 watt per meter square, then the angle between the pass axis of the first two polaroid is. So we are given that total there are 3 polarides, and the last states that it's perpendicular to that the pass axis of the first polaroid. Okay. So let us draw the approximate diagram. So our initial intensity is, let us suppose, given as I, and it passes through the first polaroid, and the output of the first polaroid will be our I0 by 2 if I0 is the input one, and the second polaroid is, okay, we need to find out the angle between the first two polarides. Okay, so for the second polaroid, let us suppose theta is the angle, and the output will be equal to I0 divided by 2 and cos of theta square. And for the last polaroid, it says that the pass angle is at an angle of 90 degree. Okay. So we can just draw a figure for that also, and angle theta, and we are given that finally, let us suppose this is given as I net, which is given to us that I net is equal to 3 watt per meter square. We are given that our I net is equal to 3, and this I net will be also equal to, and the input is given as 32, so our I naught is 32. So therefore we can say that this I naught can be further written as 32 divided by 2, and this will be cos square of theta, and multiply by, sorry, this will be our sine of 2 theta, and it is whole square, which can be written as 32 by 2, sorry, not 2 but 8, my mistake. 8, and this can be written as 2 sine square theta cos square theta, and which gives us, this goes by 4, and this goes by 8. So we are left with this as 8 sine square theta cos square theta, and this will be equal to 3, which can be further written as sine of theta. Okay, sine of theta cos of theta is equal to, this will be square root of 3 and divided by, keeping 2 here, and this will be 2. Now let me write it again. So here we can write this as sine square theta cos square theta is equal to 3 by 8. This gives us sine of theta cos of theta is square root of 3, and this comes as 4, and it will be our square root of 8, and we multiply both sides by 2. So this gives us sine of 2 theta will be equal to square root of 3, and this comes as 4, and this is 2 square root of 2 multiplied by 2. This 2 and 2 goes away, so we are left with I think it went complicated. Let me start from again. I think there is some mistake somewhere. I'm not able to figure it out. Okay, so we are given that unpolarized light and of intensity 32 watt passes through a combination Okay, let's start from again. I made a mess of it. Okay, so we given the unpolarized light is of 32 watt and there are total of 3 polarides, and it says that pass axis of the last polaride is perpendicular to that of the pass axis of the first polaride. So for the first polarizer, if its output is given as I1, then this I1 will be equal to I0 divided by 2, and this will be coming as 32 divided by 2, coming with 16 watt per meter square. And we assume that the angle between the first and second polarizer is theta. Okay, so we assume that let the angle between the pass axis of first and second polarizer is theta. Therefore, we can write the output of second polarizer. So we can say that intensity of light from second polarizer, let us suppose that is given as I2, then this I2 will be equal to our I1, and this is cos square of theta, and I1 we just found it is 16, so this becomes 16, and you have cos square of theta. Okay. And for the third polarizer, intensity of light from third polarizer, if that is given as I3, then we can write our I3 will be equal to our I2, and this comes as I2, and it will be our cos square 90 minus theta, and I2 we already know is our 16 cos square theta, so this will be 16 cos square theta, and cos square 90 minus theta is our sin square theta, and I3 is given to us 3, so we can write 16 cos square sin square theta is equal to 3. It can be written as 4 cos square theta sin square theta is equal to 3 by 4, which gives us that sin of 2 theta sin square 2 theta is equal to 3 by 4, and this gives us that sin of 2 theta is equal to root 3 by 2. Now it is correct one, and we have this 2 theta will be sin inverse of root 3 by 2. You can write 2 theta is equal to sin inverse of 3 by 2, which will be over 60 degree. Therefore theta will be coming as 30 degree. So the answer for that is our 30 degree. Next question, and it states that the ratio of intensities at 2 points P and Q on the screen of Young's double slit experiment, where phase difference between the two waves of the same amplitude are pi by 3 and pi by 2 respectively are. So here we are given the phase difference is our pi by 2 and pi by 3. Okay. And it is based on, you can say, directly the relationship or formula, and that formula is that our resultant intensity is equal to 4 times I naught square, and we have this is cos square theta by 2, and first theta is given as pi by 3, so we can write that for theta is equal to pi by 3, we have our I resultant will be equal to 4 I naught square, and this is cos square pi by 6, and sorry, not I naught square, not only I naught, and this gives us that I resultant is equal to 4 I naught. Pi by 6 is square root of 3 divided by 2, whole square. So we can write this as 4 I naught multiplied by 3 by 4. 4 goes with 4. So this comes as our 3 I naught. Second angle that is given to us is pi by 2. So we can say for theta is equal to pi by 2. We can write this R resultant is equal to 4 I naught cos square pi by 4. Pi by 4 is 1 by root 2. So this becomes 4 I naught and 1 by root 2 whole square. And let us call this one as 1 and this one as 2. 1. So we get this as 2 will be equal to 4 times I naught, and this is 1 upon 2. 2 goes by 4, so which gives us 2 times I naught. And we need to find out the ratio. So ratio we can write that our I is a 1 to I resultant 2 will be equal to, we have this as 3 I naught, 2 I naught, I naught and I naught goes away. So the ratio comes as 3 by 2. So option number 3 is the correct one. Option 3 is correct. Next question states that in a Young's double slit experiment, the ratio of the amplitude of light coming from the slits is 2:1. The ratio of the maximum to minimum intensity in the interference pattern is. So we are given amplitude is ratio as 2:1, and we know the relationship or direct formula between maximum minimum intensity with respect to their amplitudes. So we are given the ratio of their amplitudes, that is our A1 upon A2 is given as 2 by 1, and we also know that our maximum to minimum ratio, it is given as A1 plus A2 whole square, A1 minus A2 whole square. So we can write this as I max to I mean will be equal to A1 upon A2 plus 1, A1 by A2 minus 1, and their respective whole squares. So this gives us A1 by A2 is our 2, so this becomes 2 plus 1, and 2 plus 1 and 2 minus 1, their whole square. So this becomes 9, and 9 is to 1. So option number 2 is the correct one. Two is correct. Next question, and it states that a single slit of width A is illuminated by a monochromatic light of wavelength 600 nanometer. The value of A for which first minima appears at theta is equal to 30 degree on the screen will be. And we have to find out here angle, and it is said to be the first minima. And we know for the first minima, A sine of theta is equal to lambda. You can say for first minima, we have our A sine of theta is equal to lambda, and theta is given to us 30, a is also given, we need to find out a, lambda is given to us. So we can say a is equal to lambda upon sine of theta. Lambda is given as 600 nanometer minus 9, and here we have sine of 30, and this is sine 31 by 2, this comes as 12, so we can write this as 1200 into 10 to the power minus 9, or we can write this as 1.2 micrometers. So option number 2 is the correct one. Two is correct. Next question. It states that in Young's double slit experiment, the position of the fifth bright fringe from the central maxima is 5 cm. The distance between the slits and the screen is 1 meter, and the wavelength used of monochromatic light is 600 nanometer. The separation between the slits is. So here we have to find out the small d. And we know that for the nth, you can say bright fringe, for nth bright fringe, the relationship is y of n is equal to n lambda d upon small d, and we need to find out here small d, so we can write small d is equal to n lambda capital D divided by y of n, and we know all these values, we simply substitute them, we get d is equal to n is our fifth, lambda is given as 600 nanometers, 1, and y of n is given to us as, distance is given to as 5 centimeter, 10 is power minus 2, and this will be coming close to 5 goes with 5, and this is 6, 10 is power minus 7, or 600 10 is power minus 7, and right, this will be equal to 600 into 10 to the power minus 7, or this can be equal to our 60 micrometers. So option number A is the correct one. Option A is correct. Next question. It states that in Young's double slit experiment, two slits are illuminated by a wavelength of 800 nanometer. The line joining A1P is perpendicular to A1A2 as shown in the figure. If the first minimum is detected at P, the value of slit separation A will be. So we are given a figure. So we have a point P, and this point P is having a first minimum, and here AP is perpendicular where the A2 is at some angle. This is point P which is having a first minima. Based on this we have to find out the distance between A1 and A2. And we know that the condition for minima is our A2P minus A1P should be equal to lambda by 2. We start from there. Condition for first minima, and we can write the formula that A to P minus A1P will be equal to lambda by 2, and for A1P this can be written as A square plus D square and its square root, because this distance is over D, and we can find out this distance because angle is given 90 degree, so this will be A square plus D square, and even P is nothing but a capital D lambda by 2, and we can use a binomial theorem to sort it out, and we can write it as, taking D as common, we are left with 1 plus A square by D square and 1 by 2 minus T is equal to lambda by 2. This gives us D, and this we have 1 plus 1 by 2 A square D square, neglecting the higher order terms, minus T is equal to lambda by 2. And if the open the bracket, we get this as D plus 1 by 2, and we have this is A square upon D minus T is equal to lambda by 2, and this T and D cancels out, so we get here that our A square by 2D is equal to lambda by 2, and 2 and 2 also goes away, so we are left with that our A will be equal to square root of lambda times capital D. We substitute the values, we get this as 800 multiplied by minus 6 and multiplied by 50, so we get our A will be equal to 0.2 millimeters. So this is 0.2 millimeter. Option C is the correct one. C is correct. Next question, and it states that as shown in the figure, three identical polarized P1, P2, P3 are placed one after another. The pass axes of P2 and P3 are inclined at the angle of 60 degree and 90 degree with respect to P1. The source S has an intensity of 256 Weber per meter square. The intensity of light at point O is dash. So here we are given that source S, and we need to find out the intensity at this point O. Okay. So for the first polaroid, our first polaroid, if its intensity is given as I1, then this I1 will be equal to I0 by 2, and it is given 256, so this becomes 256 divided by 2. And for second polaroid, if output is given as I2, then this will be equal to I1, and we have this as cos square theta, and for the theta here is 45 degree, therefore we can write that our I2 will be equal to I1 is 256 divided by 2, and we have cos square of 45, sorry, cos square 60, not 45, and that is our 1 by 2, 1 by 2 is 1 by 4. So this becomes 256 divided by 2 multiplied by 1 by 4. And we have the third polaroid. So we have for third polaroid, that is of I3 will be equal to our I2, and this will be cos square of theta. Here theta is our 90 degree, but the angle of 90 is given to the axis of P1. Okay. So here this theta angle will be between the polaroid third as well as polaroid second. Therefore we can write that our I3 will be equal to I2, we just found out is our 256 multiplied by 1, 4, and this becomes our cos square of 30, and we can cos of 30 is square root 3 divided by 2 and it whole square. So we can write this as 256 multiplied by 1 multiplied by 3 and divided by 2 multiplied by 4 and multiplied by 4. So we get our I3 will be equal to 24. So answer is 24. Next question. Unpolarized light is incident on boundary between two dielectric media whose dielectric constant is 2.8, that is medium 1, and 6.8, medium 2 respectively, to satisfy a condition so that the reflected and refracted rays are perpendicular to each other. The angle of incidence should be tangent inverse 1 plus tan divided by theta whole raised to power 1 by 2. The value of theta is given. Dielectric media is having a relative dielectric constant, relative permeability is given as 1. Okay. And here we are given that both reflected ray as well as refracted ray should be perpendicular to each other. Okay. So in this case, we are going to make use of the Brevister's law. Okay. So we are given dielectric constant of medium 1. So we are given dielectric constant for medium 1. Let us suppose that is given epsilon 1, which is our 2.8, and we have medium 2. Let us suppose this is epsilon 2, which is given as 6.8. And we are also given the relative permeability for both media. Relative permeability for both media, it is given as mu of r, and that is equal to 1. And we already know the relationship between the dielectric constant and relative permeability, that is equal to our dielectric constant multiplied by relative permeability. Okay. So we have two mediums, and we know the relationship of that our n is equal to square root of epsilon naught and multiply by mu r. Okay. And here n is our refractive index, and epsilon is our dielectric constant, and mu r we know is our relative permeability. So we have two mediums. We can divide this, you can say, formulation into two parts. For medium 1, we can write this as our n1 will be equal to E1 mu r. Mu r is same for both, so this becomes 2.8 multiplied by 1 is equal to square root of 2.8. And we have medium 2. This gives n2 epsilon 2 mu r and square root. This comes as 6.8 multiplied by 1 and square root, giving a square root of 6.8. And for reflected ray and refracted ray are perpendicular to each other, so we can use the Brewster law. So we can say from Brewster law, if the angle of incident is I, so tangent of I will be equal to n2 upon n1, and this comes as 6.8 divided by 2.8 and its square root. And we can just simplify the expression. We get tangent of I will be equal to, this comes 68 upon 28, and that will be coming as 17 upon 7 and its square root. And we need to modify this equation as per this particular equation, especially the angle part, that is 1 plus tangent divided by theta. Then we can determine the theta. So we can write this as 7 plus 10 divided by 7. This comes as 1 plus 10 divided by 7 and whole raised power 1 by 2. And we get our I. From here we can write our I will be equal to tangent of inverse, that is 1 plus 10 upon 7 whole raised power 1 by 2. And the given expression is tangent of inverse 1 plus 10 upon theta whole raised power 1 by 2. So this gives us that our theta is equal to 7. So value of theta is equal to 7. Next question. And it states that in Young's double slit experiment, two slits S1 and S2 are d distance apart, and the separation from the slits to the screen is capital D as shown in the figure. Now if two transparent slabs of equal thickness 0.1 millimeter but refractive indexes of 1.51 and 1.55 are introduced in the path beam, lambda is 4000 angstrom from S1 and S2 respectively, the central bright fringe spot will shift by dash number of fringes. So we are given the figure. We have two, you can say, slits S1 and S2, and for point P, which is our central maxima, and we have two slabs, thickness is same but the refractive indexes are different. And from the figure we can just draw one approximate that this be the center. So this is point O. So this is our geometrical center. And in upward direction we have our Y, and this P is our, you can say, central maxima or central bright fringe. So this P will be our central maxima, or we can call it a central bright fringe. Bright fringe. So we can say the path difference at P at P, if that is given as delta x, then we can write delta x in terms of the glass slab, which will be our mu2 minus mu1 and multiply by T. These values are given to us. So mu2 is 1.55 minus 1.51 and thickness is our 0.1 millimeter. Therefore, we can write that our delta of x will be equal to, this will be coming as 0.04 into 10 to the power minus 4, or we can write 4 into 10 to the power minus 6 meters. And we need to find out the y. So y will be equal to the path difference, and this is capital D divided by small d. So this is a 4 into 10 to the power minus 6 10 to the power minus 6 capital D divided by small d. And so here y is our nothing but you can say the distance of central maxima from the geometrical center, which is indirectly the representation of the fringe width. Therefore, we can write that our y is the distance of central maxima from geometrical center. Therefore, we can say our fringe width, that is a beta, will be equal to lambda capital D divided by small d, and lambda we already know, that is our 4000 angstrom, and this is your 4000, or we can write into 4 into 10 to the power minus 6 capital D divided by small d, and you can say the number of shift will be equal to number of shift, if given as n, this will be equal to y upon beta, and y we found out is our 4 into 10 to the power minus 6, and beta is 4 into 10 to the power minus 7, and ratio d and capital D both are going to cancel each other. So these two terms cancel, 4 and 4 goes away, so we get the value of n is equal to 10. Okay. This is 7. So n is equal to 10. So we have 10. Next question. we are given that in a Young's double slit experiment, the intensity at 2 points for the path difference lambda by 4 and lambda by 3, lambda being the wavelength of light used, are I1 and I2 respectively. If I0 denotes the intensity produced by each one of the individual slits, then the ratio I1 upon I1 plus I2 divided by I0 will be equal to. And we are given the path difference is, sorry, it has to be path difference is given to us as lambda by 2, and we can use the formula for the, you can say, the phase difference, and we start with that our I is equal to 4, and this is our I0 cos square, and this is our delta phi divided by 2, and the path difference lambda by 4 and lambda by 3. Okay, so we can write this into two parts. We can say for first wavelength, that is our lambda, when the I1 will be equal to over 4 times I0, and this comes as cos square, and our phase difference, that is delta phi, will be coming as pi by 2. So we can write this as pi by 4, and pi by 4 is our 4 I0, pi by 4 is 1 upon square root 2, so this comes 1 upon 2, and this 2 goes by 4, so we get this will be equal to 2 I0. Similarly, we can write that our I2 will be equal to 4 I0 cos square, and we get this as pi by 2 pi by 3, which gives us I0, and we have to find out I1 plus I2 divided by I0. Okay, so it means I1 plus I2 divided by I0, and I1 plus I2, this becomes twice I0 divided by I0, this comes as 3. So 3 is the ratio. Next question. And it states that two polarides A and B are placed in such a way that the path axes of polarides are perpendicular to each other. Now another polaroid C is placed between A and B, bisecting angle between them. If the intensity of unpolarized light is I0, then the intensity of transmitted light after passing through through polaroid B will be. So we have three polarides A, B and C. Okay. And unpolarized light is given as I0, and first polaroid is our A. So we can say that for polaroid A, if its intensity is given as IA, that will be equal to I0 by 2. And C is in between B and C, and it is bisecting their axis. Therefore, we can say for polaroid C, and that will be equal to our IA, and we have this as cos of square and 45. IA is our I0 by 2, and 45 is our 1 by 2. So this we can say that is IC will be equal to I0 by 4. And now we come to the finally the polarized B, you can say for polarized B, that is our IB, will be equal to IC, and cos square of 45, IC is our I naught by 4, and 45 is square is 2, 1 by 2 rather. Therefore we get that our IB, which is our final, is equal to I naught by 8. So option number C is the correct one. Option C is correct. Next question. It states that two light waves of wavelength 800 and 600 nanometer are used in Young's double slit experiment to obtain interference fringes on the screen placed 7 mm away from the plane of slits. If the two slits are separated by 0.35 mm, then shortest distance from the central bright maxima to the point where bright fringes of two wavelengths coincide will be. So we have to find out the bright fringes of both the wavelengths, and they should be coinciding, and the shortest distance. So we know that we have two wavelengths, so we can say that our, let us call this as beta 1 will equal to lambda 1 capital D small d, and our beta 2 will be equal to lambda 2 capital D and small d. And we are given that the slits are separated by a distance of slits are separated by a distance of 0.35, and it is 7 mm away. Okay, so we substitute the values, we get beta 1, lambda 1 is our 800, 10 to the power minus 9, and we have capital D, that is 7, and small d is 0.35 into 10 to the power minus 2. So this gives us that beta 1, we can just write it in the millimeters. Beta 1 will be coming as 16 millimeter. Similarly, we can write our beta 2 will be equal to our 600 10 to the power minus 9 multiplied by 7, and this is 0.35, which gives us 12 millimeters. And we need to find out the smallest excuse me please, you can say the shortest distance. So for the shortest distance, we find out the LCM between these two values, 16 and 12. So you can say LCM of beta 1 beta 2, which means LCM of 16 and 12 is equal to 48 millimeter. So this is the final answer, that is 48 millimeter is the shorter distance between the two. Next question, and it states that n polarizing sheets are arranged such that each makes angle 45 with preceding sheet. An unpolarized intense light of intensity I is incident into this arrangement. The output intensity is found to be 1 upon 64. The value of n will be. So here we are given that initial intensity is I, final intensity is I by 64, and the angle is 45 between the successive, and there are n number of sheets. So you can say for first sheet first sheet, that is our I1, will be equal to our I divided by 2. For second, that is our I2, will be equal to our I1. Angle is given as 45, this is cos square of 45, and this comes as I1 by 2, or we can say I by 4. And from here we can easily see that this can be written as I upon 2 raised to power 1, and this can be written as I upon 2 raised to power 2. So it means for nth sheet, I of n, this will be equal to I 2 raised to power n, and this is given as 1 upon 60, I upon 64. So this gives us that 2 raised to power n is equal to 64, giving us that the value of n will be equal to 6. So option number B is the correct one. B is correct. Next question, and it states that as shown in figure, in Young's double slit experiment, a thin plate of thickness T is equal to 10 micrometer, refractive index mu is equal to 1.2 is inserted in front of slit S1. The experiment is conducted in air where mu is 1. Uses a monochromatic light of wavelength lambda is equal to 5 nanometer. Due to the insertion of the plate, the central maxima are shifted by a distance of x b0, where b0 is the fringe width before the insertion of the plate. The value of x is, and here it is given that the central maxima is shifted by x b0, and we know the formula that the fringe shift is given by, you can say that the fringe shift that is given as T mu minus 1 and divided by lambda and multiply by b0. Mostly it's written b, but here specifically is written b0, so we have written as b0. Okay, and we know all the values, so we substitute. T is given as to 10 micrometer, 10 is to the power minus 6. Refractive index is given to us as 1.2 and minus 1. Wavelength is given as 500 nanometer, 10 is to the power minus 9 multiplied by b0, and this will be coming as 0.2 and 10 is to the power 7. Okay, so we can write this as 2 upon 5 multiplied by, this is 10 raised to the power, this 0 and this 0 goes away, so we have 10 raised to the power minus 7 and 10 raised to the power minus 9, and this comes as, okay, and this is our 10. Okay, and we are left with minus 6 plus 9. I think this looks good. Multiply by b0. So we get this as 2 upon 5 multiplied by, this becomes 3 divided by 10, and this goes by 10, 10, and this is our, I think there is, let me check, one second. 10 raised to power 1.2 thickness is given to us as 10 micrometer. So we have 10 into 10 raised to power minus 6 and 1.2 minus 1 and divided by 5 into 10 raised to power minus 7 and multiply by B naught. And this we are left with 10 raised to power minus 5 divided by 5 into 10 raised to power minus 7 into 0.2. And this comes as 100 divided by, now it's correct, I made a mistake somewhere, multiply by B naught. So this is our 100 divided by 5 multiply by 2 divided by 10. This goes by 0 and this goes by 2, so we come this as 4 and 4 times beta naught, so this is our x times beta naught. Therefore we get that our value of x is equal to 4. So value of x is 4. So I think this completes, yeah, so this was part second for the year 2023 means questions. Okay, so both the parts are completed from the year 2023. The question from advanced as well as some question from mains were done in part 1, and this is the part 2 which consists of only the mains question. So this completes all the questions. Thank you.